Hello guys, today we are exploring a fascinating circuit that you'll find incredibly useful in many applications, which is single supply low side unidirectional current sensing circuit. Well, the name is big, but the circuit is small only. Let's dive in. First off, let's talk about the current sensing. Imagine you have a water pipe running from a reservoir and you want to measure how much water is flowing through it. In electronics, measuring the flow of electric current is crucial for monitoring and control circuit, just like measuring the flow of water. Current sensing helps us understand how much current is flowing through a particular part of circuit. This is important for applications like battery management systems in electric vehicles, where we need to monitor the current to ensure safety and efficiency. It's special because it's single supply, low side, and unidirectional. What does that mean? Well, single supply means it operates with just one voltage source, making it simpler and more efficient. Low side refers to its placement on the ground side of the load, which means it is easier to measure the current without affecting the rest of the circuit. And unidirectional means it measures the flow of current in one direction only, perfect for straightforward applications. Let's see what the circuit looks like. Our design goal is to detect a load current up to 1 ampere and convert it into a readable voltage. The key players here are a shunt resistor. It creates a small voltage drop proportional to the current. An operational amplifier. It amplifies the voltage drop across this shunt resistor. Some peripheral resistors R2 and R3 to set the gain of the amplifier. Let's dive deeper into these components. The shunt resistor R1 is chosen to create a small but significant voltage drop when current flows through it. Here we'll select op-amp TLV9062, which is crucial because it has rail-to-rail output and input, meaning it can handle a wide range of voltages, making it perfect for this application. R2 and R3 are precision resistor that set the gain of the amplifier. The gain determines how much op-amp amplifies the voltage drop across this R1. So, as mentioned, we need to design a circuit which is able to sense 1 ampere current, which should convert this into proportional voltage up to 4.9 volts. For that, we'll supply 5 volts VC supply and 0 volts to VEE of this op-amp. When current flows through R1, it generates a small voltage drop. The op-amp then amplifies this voltage. For our circuit, we want an output swing from 50 mV to 4.9 volt. By adjusting R2 and R3, we can set the amplification factor to achieve this range. Here's the math behind it. The maximum shunt voltage we input max is 250 mV when the current is at its maximum of 1 ampere. Our desired output voltage we output max is 4.9 volt. The gain is calculated as maximum output voltage divided by maximum input voltage, which gives us gain of 19.6. So, using standard resistor values, we set R2 as 715 ohms and R3 as 13.3 kilo ohms to achieve this gain. Think about a smart home. To monitor the energy consumption of your devices, you need accurate current sensing. This circuit could be integrated into smart plugs to keep track of power usage, ensuring your devices are energy efficient. Just like a water meter at home tells you how much water you're using, this circuit monitors the electric current. When designing this circuit, we have to keep few things in mind. First is component tolerances. We have to ensure our shunt resistor's tolerance is tight to minimize errors. For high accuracy, a high tolerance of 0.1% is highly recommended for R2 and R3 as well. Second is capacitive loads. We have to avoid placing capacitive loads directly on the op-amp's output to maintain stability. Adding a small capacitor in parallel with R3 can help stabilize this circuit. Additionally, we have to pay attention to the phase margin of our circuit. Using high-value resistors can degrade the phase margin and introduce noise. To maintain sufficient phase margin, we have to ensure the zero created by the gain setting resistors and input capacitance is greater than the bandwidth of the circuit. Well, we can use simulation tools like Tina from Texas Instruments to simulate the circuit as well. You can check the description for more details. And there you have it, a single supply low side unidirectional current sensing circuit that's both efficient and effective. I hope you learned something new from this video. Don't forget to check the description for references and simulation files. If you found this video useful, hit that subscribe button as well.